Started. Okay, hello everybody. This is part 3 of the mini course on computer programming and biology as part of the NMCB course. And in previous talks, we talked about the computing environment and in particular the Unix environment. And we talked on standard tools available on Linux and Unix like systems and also the Unix philosophy of programming, so to speak. Second talk, we talked about basics of computer programming and how to divide a task into a structured list of functions and things like that. Today we'll be talking about algorithms and efficiency. And to repeat what we said the last 2 times, one learns this only by doing. In particular, algorithms is typically a whole semester course in computer science courses, and we're just giving a very rough overview. The point of algorithms is to understand how to do something efficiently, and we'll be talking about a few standard algorithms here, and one side of it is to implement them yourself, but the other side is if you're given a new task that nobody has done before, can you think of a good way to do it? And the only way to do that is to read up a lot about existing algorithms so that you get a feel of the common features in algorithms that help you do things efficiently. We'll be talking to a couple of those strategies later in the talk, but we can only scratch the surface. So as I said, previous talks talked about the Unix philosophy in particular, and now we'll talk about algorithms. So what is an algorithm? An algorithm is a process or a set of rules or a sequence of steps by which to do a calculation. So typically computer scientists don't describe algorithms as programs, but just as some sort of recipes in a language that you might call pseudocode. So basically they might tell you basically how it works, and they might prove things about its efficiency. To take perhaps the simplest possible example, one of the simplest examples you might have come across, how do you calculate the factorial of a number? The factorial of a number n is the product of all integers from 1 to n, and in the previous lecture we talked about how to implement this function in Python, but today we'll talk about the complexity. So we won't use any actual programming language, and we won't use all the error detection stuff that we did last time. This is the essence of the function. If n is equal to 0 or n equal to 1, return 1, otherwise return n times the factorial of n minus 1. So this is the basic of the function. Now we ask, how do you analyze the can you give me one moment, sorry, the factorial function in pseudocode. What we want to ask is, if you call it for an input m which is reasonably large, how many steps does this function take? In order to calculate that, you can work through how this thing goes. If m is not 0 or 1 and m is much greater than 1, so it is not. So you when you call a function on a real computer, what you're doing is you're abandoning this current state and jumping somewhere else. So you have to save the current state, in particular the value of the variable, you have to save it somewhere. It's saved in a data structure called the stack, and then when you return from this function call, you pick up this variable from the stack and do whatever you need to with it and proceed. So what happens here is m is large, so it is not 0 or 1, so you will push the value of n which is equal to m onto the stack and then call the function itself. And m minus 1 is also not 0 or 1, it will push the current value onto the stack and call itself, and it will keep on doing that until it reaches the value which is 1. When it reaches the value 1, it no longer calls itself, it returns 1. So then it pops the stack at the next level to get the value 2 and multiplies by the previous value. Then it pops at 3 and multiplies the previous value until it reaches back to the top, and then multiplies by all the previous values, and finally it returns the value it gets. So how many steps does it take? It is some constant times m, because all these recursive function calls take roughly m steps, give or take 1, and after you return from the function calls also you take about n steps. So the number of operations is some constant times m. Just in passing, though we won't talk about it in this course, there are costs, as I said, associated with calling a function. So every time you are calling yourself, you are pushing your state onto the stack, and then you're popping and you're jumping your program pointer somewhere else. So there are functional programming languages, languages that focus on treating everything as a function, where recursion is actually encouraged. So how do they deal with this? In this case they can't, but you can rewrite this function in such a way that the last return statement only returns its own call. So if you had a recursive function such that the return consisted of a call to itself and not anything else, then at that point you don't need to save any state. You can throw away your state, and you don't need to put anything on the stack. Even better, the compiler can actually optimize this function into something like a for loop, which is how you normally do it. So if you use a programming language like Scheme or Haskell or a bunch of languages like that, and if you rewrite this function in what's called a tail call optimized way, such that there is nothing else happening, only a call to the factorial, which you can look it up, then you can make this function as efficient as this example. So here you are simply, the first two lines are the same, otherwise you are running a for loop and multiplying all the integers from 2 to n and returning the value. This also takes some constant size, the input size m, but that constant is much smaller compared to the previous slide. Now in algorithms you often don't care about constants as such, but you do care about complexity. So in terms of complexity, here is another example that we talked about last time, Fibonacci numbers. Supposing in the sequence where every number is the sum of the two previous numbers, you want the nth number in the sequence. So what is, for example, the 100th Fibonacci number? You could think of writing a function like this along similar lines. If n is 1 or n is 2, then you return 1, else return the sum of the two previous numbers. But the question is, so it is a very simple short function to write, but how long does it actually take for an input m which is greater than 1? So you can try working it out verbally, that you call it, for example, with 5, it will call itself with 4 and 3, but then each of those calls will then call itself again. So what you do is you draw what's called a call graph. This figure is taken from Abelson and Sussman, which is a book worth reading. So supposing you call this function with the value 5, it calls itself with values 4 and 3. Now 4 calls itself with 3 and 2, but 3 calls itself with 2 and 1, and so it cascades down until you are calling itself with 1 or 0, right. So the total number of calls you can see is growing pretty rapidly. In fact, you can show that the number of steps required is exponential in m, that is, it is something to the power m. So it is what to the power m? You can prove that the number of leaves on this graph is exactly equal to the next Fibonacci number. So for example, this graph has 8 leaves, which is in fact the next Fibonacci number. It is not difficult to prove that this is always true. So the number of steps you need is proportional to the number of leaves. So you also have all these intermediate steps to do. And the mth Fibonacci number you can show is the nearest integer to this number. Phi is called the golden ratio, and phi to the power m divided by square root of 5. So it is roughly 1.6 to the power m times some constant. So this is very bad news. It means that if you run it for like even modest values of m, this function is not going to end in reasonable time. So I am going to talk about something called big O notation, which you will come across anytime you read a computer science textbook. This summarizes how much time an algorithm takes. So supposing you have calculated that the algorithm actually takes a time t as a function of n, but you don't really care about the details of t in most cases. You have some other simpler function f of n, for example n squared or exponential or whatever. You say t of n is big O of f of n if there exists constants c and n naught, such that for any n greater than n naught, the time taken by this algorithm is less than c times this f of n. So it means that the running time is bounded from above by this function f of n. It could be much less, but it is at least this much for large n. T of n is big omega of f of n if similarly there exists constants such that T of n is greater than this. So, it means T by n takes at least this long to run, it may take longer. And the big theta notation is used if both of the above are true. That means it's bounded both from above and from below by a function of order f of n. And small o is used if it is bounded from above but not from below, that is we know that it is not bounded from below. So, in this case this sounds a bit abstract. The point is, supposing you have calculated that an algorithm that you wrote takes 10n squared plus 5n plus 3 steps. You normally say it runs in order n squared time. You do not care about 5n plus 3 and so on, because you can write 10n squared plus 5n plus 3 is less than 10n squared plus 5n squared plus 3n squared for any n greater than 1. So, it is some constant times n squared, so it is like order n squared. But this algorithm is also big omega of n squared because this number is greater than 10n squared. So, for both of the first two conditions you have this criterion satisfied. So, this algorithm is in fact big theta of n squared. So, in the previous examples both versions of the factorial function were big O of n. In fact, they were big theta of n because it is bounded both from above and below by the size. The Fibonacci function as we wrote it is exponential in n. Now, big O and big theta is a little tricky when you talk about exponentials because you have to ask which exponent. Normally in mathematicians write e to the power x is exponential, computer scientists might write 2 to the power x. So, what to the power x? And it is not exponentials are not bounded above and below by other exponentials necessarily, but you can say that if this is the exponent, then it is bounded from above by some exponential, it is bounded from below by some other exponential. So, you could write this is basically exponential in n without specifying the exponent, and the point is that any exponent greater than 1 it is bad news. So, the following function for Fibonacci numbers is linear in m, which is simply if n is 1 or 2 return 1, otherwise explicitly calculate the next one from the initial numbers. So, f1 is 1, f2 is 2, m is 3. So, the potential next Fibonacci number is 3. Is m less than the input? So, if I call this function with n is equal to 3, this entire thing will not be skipped and I will return f2. So, f2 will be 3. If I call m with a greater function, it will keep incrementing m while incrementing these functions f1 and f2. So, f2 is going to be the Fibonacci number you care about and f1 is going to be the previous one. And this is just shorthand for saying update both of them. Some computer languages accept this and some do not. And after this is done, you return f2 and this runs linear time. So, why is all this important? So, supposing this is from Kleinberg and Tardos. Supposing you have a running time for different algorithms on a function performing 1,000,000 instructions per second and you have input sizes of this. If your algorithm is of order n, then you will take about 1 second for input size 1,000,000. N is the lowest number given here. For certain examples you can even have log n running time, but so that will be really tiny. So, supposing your algorithm takes n times log n running time, this also is pretty good for most reasonable input sizes. By the time you get to 1,000,000, instead of 1 second you take 20 seconds because the log to the base 2 of 1,000,000 is about 20. Supposing it was n squared, we will come to algorithms that have n squared running time, then instead of a second you will take 12 days, and if you had n cubed you will have many years. But supposing you had a very modest exponential, just 1.5 to the power n, then even for input size of 50 you take 11 minutes and for input size of 100 you take 12,000 years. And if you have like 2 to the power n, you take years even for input size of 50. But this grows, as you know, exponentials grow very, very fast. And for n factorial, which is the worst of all, it is like n to the power n times square root of 2 pi n and so on. So, n to the power n is like the worst exponential, worse than any exponential. So, I am not personally aware of which algorithms take this long, but there probably are some, but you do not want to do that unless there is no alternative. Okay, so the previous Fibonacci example might have given you the idea that recursion is bad, especially if you are recursing more than once. So I want to give you a counter example. How do you sort a list of numbers? This is a fairly standard textbook exercise. Unfortunately, most beginning textbooks start with a method called bubble sort. So here's bubble sort, and let's look at what it does and analyze the running time of this program. So bubble sort basically takes a list, then it starts with the beginning of the list, let's say n is equal to 1 initially, and it compares with every other member of the list, that is n plus 1, which is starting from 2 till the end of the list. And if those elements are less than your n is equal to 1 element, it exchanges them. So at the end of the n is equal to 1 loop, you will have brought the lowest element to the first position. Then you go to n is equal to 2, and again you, at this point n is equal to 2, you know n is equal to 1 is less. So n is equal to 2, you look at all the remaining elements and again exchange them, and at the end of this, the n is equal to 2 position will have the minimum element, and you keep on doing that. So it is as if the minimum elements are bubbling down the list until you have gone through the entire list. So it is easy to implement, and at the end you return the list. So what is the running time? You have got 2 for loops, each of which is of roughly the length of the list. So it is of order n squared. In particular, it is since you are comparing all pairs of elements, it is n into n minus 1 divided by 2, but you do not care about constants, so you say order n squared. And n squared, to go back to the slide, means that if you could do it for example in n log n time, you could sort a list of million numbers in 20 seconds, but bubble sort would take you 12 days to do the same thing. So is there an algorithm to sort numbers in n log n time? In fact, there are several, and I am going to talk about only one called Quicksort, because it is very easy to describe and not very difficult to understand where the log n comes from. So the function is basically defined like this, and it is a double recursive function, as you see. You take a list, and if the length of the list is 1, that means there is only one element in the list, then you just return it, there is nothing to do. Otherwise, you take the first element of the list, it is called the pivot, so we call it P. Then you take all the elements of the list from the second onwards which are less than or equal to P, and you put them in a new list called list underscore L. And you also take all the elements in the list that are greater than P from 2 onwards, that is not including this pivot element, and put them in list underscore right. And then you return the sorted list underscore L and P, and then list underscore right. So you can tell that if Quicksort is doing its job, this is a sorted list, but what it is doing is it is calling itself at this point. Now the claim is that this has an average running time of n log n, and in this simple form its worst case is actually order n squared, and the worst case occurs if the list is already sorted. So we will come to that, but why is it n log n on average? Because supposing the list is really random, it is kind of scrambled, then the first element, the pivot, could be anywhere in the list. So list underscore L and list underscore R are roughly each half the size of the original list. Now the running time for this step is you are taking the pivot, and then the time to sort this list. So each of these steps is of order n, because you are filtering the list to find out which elements are greater, which elements are less. So the n basically comes from here, and so each time you are doing selection of order n, and you are doing it again and again, but how many times are you doing it? Supposing your list is reasonably random, then the first time you call it, you will be sorting a list of half the size and another list of half the size. Next time you will be sorting a list of 1/4, 1/4, 1/4, 1/4, and so on, it goes down. So the number of times you will need to recurse is of order log n. log to the base 2n in particular. In the ideal case, it will be exactly order n to the base 2n, n log base 2n, and typically it will be not very much worse than that, though that's a sort of probabilistic statement. Now, this is a very simple implementation. In practice, people do, the most efficient versions of Quicksort are done without recursion. So, you create an auxiliary list and you there are ways to do this without recursing, which we won't get into, but that can bring the prefactors down a lot. So, recursion adds a constant time here, and you want to bring some of those things down. There are a bunch of other sorts like heap sort and so on, which actually have a worst case time of n log n, but on average their prefactor tends to be bigger than Quicksort. So, their worst case is better, but their average performance is often not as good. So, Quicksort is still very widely used in various forms. This divide and conquer strategy is very common in algorithms. So, here is a simpler example. How do you find the position of an item x, that is I is equal to index of x, which means the ith element of the list L is x, given an unsorted list. So, I have given you a list of 100 numbers which are not sorted, and I want to find out where the first position of the element x, let us say the number 3, occurs in that list. So, if the list is not sorted, there is no other way to do it. You have to check the first element, there is no match, you check the second element, and you keep otherwise check the third element, and so on until you match. And the time taken is order of n, where n is length of the list. What if the list is sorted? Then you can do it much better by what is called bisection. So, you take the list and you got an element, check the halfway point of the list. So, if this element, well, if it matches, then you just return it, that is your answer, but probably it will not match. So, if it is greater than x, if the halfway point is greater, then your element is in the first half of the list, and now you bisect that. Otherwise, on the second half of the list and you bisect that. So, each time you take the midpoint of the interval you have until you converge on your element, and the time taken is going to be of order log to the base 2 of n. So, if you got a list of 1,000,000 elements, this would take you of the order of 1,000,000 each time, but this will take you of the order of 6 or 7 steps. So, it is a huge difference. So, as we already said, the cost of sorting a list would be order n log n. So, if you are just need to find one element in a given list, you still should do this. But supposing you need to repeatedly find an element in a list, maybe you should sort the list while keeping track of the original index position of the elements. Then you find the element here and then you look up the original index position, for example. So, this is something you can do. So, another example that I do not have a slide for, but I heard it in a talk by Mehud Amir some time back, is one of these toy problems that computer scientists like to talk about. It is a very possibly unrealistic problem. It is supposing you have a factory that produces glass balls, hard glass balls. You drop them, they do not break up until some height, and then they will break. And you have a tower of n floors, so maybe 100 stories or something, and you want to find the minimum level of the tower from which the ball will break if you drop it. And you are going to assume things like when you drop it and it does not break, it does not weaken or anything like that, either it breaks or it does not break. So, the factory owner gives you one ball and says find the minimum height of the tower from which if I drop it, it will break. So, if you are given only one ball, there is nothing you can do except try from the first story. If it does not break, try from the second story, and so on until you go to the nth story and it breaks, and you say that is your answer. Supposing the tower owner gives a ball factory owner gives you as many balls as you want. So, you can use as many balls as you want, just tell me which level it breaks at. Then you can use the bisection method, that you take a ball halfway through the tower. If it breaks, then you take halfway at the lower half, it does not break, halfway to the upper half, and keep doing that, and then you can do it in log n, where n is the number of tower levels. Supposing the owner gives you 2 balls, not 1 and not as many as you like, but 2. then what is the best you can do? So, I leave that open, or maybe I will just give the answer. The answer is square root of n. So, if the tower has 100 stories, then you can do it in 10 tries, not 100 tries and not log of 10, which is roughly 6 or 7, but 10 tries, which is not so bad. This is a very famous algorithm that uses this kind of divide and conquer strategy to get a log where you might get a normally expect linear, or in this case quadratic answer. So, the Fourier transform is so a Fourier series is given a function, it breaks it up into sines and cosines, and a Fourier transform, a discrete Fourier transform is basically a discrete kind of a Fourier series. It is of extreme importance in signal processing and so on. When you have a sound wave, you want to filter out certain frequencies and so on, the easiest way to do it in the digital domain is to Fourier transform it and reduce the things you want. So, supposing you have a sequence of numbers x0, x1 till xn minus 1. So, we are going to use 0 based indexing here, it is more convenient. The Fourier transform of the series, imagine that these numbers are samples of a waveform, for example, they are samples of a sound, and you can define big X as the Fourier transform. It is defined as small x n times e to the power 2 pi by n and k. So, each of these is for each value of k, k goes from 1 to n minus 1, each of these is like one normal mode of the system, and the system can be written as a sum of normal modes in this way. Now, you want to calculate this, and naively this is order of n squared, because you have to calculate for each value of k. So, you have to calculate an array of length n, but for each element of that array you have a sum here that goes n times. So, you would think that you need n squared operations to do this. In fact, you do not, you need n log n operations and the method is called the fast Fourier transform. It was apparently originally discovered by Gauss, but it was not really known because he published it in some form of Latin and people did not read it. It was rediscovered by Cooley and Tukey in the 1960s, and that is when the field of digital signal processing took off. The idea is this: supposing n is even, then you can rewrite this sum in terms of odd and even values of n. So, the odd values of n will be like 2m and the even values will be like 2m plus 1. So, just rewrite the sum separating into odd terms and even terms. Now, the odd terms, you can bring this 2m down to the denominator and it looks like this, and so there are n by 2 terms in this sum. So, these are all the even elements of this sum, sorry, this is even elements of the sum, there are n by 2 terms, and this looks exactly like a regular Fourier transform, right. And the odd terms has an extra exponential factor because of this plus 1, which you can pull out, and then this also looks exactly like a regular Fourier transform of half the length. So, without going into the details, the idea is to Fourier transform each of these separately, and they will again have odd and even pieces, and so you keep on dividing it by 2 until you reach things of length 1 whose Fourier transform is basically itself, and then you recombine them. There are various clever things here that I am not getting into, but eventually the complexity of this algorithm is n log n, because each time you are dividing it in 2 and the number of divisions you need to make to reach a very small array is of order log n, and then the cost of the transform is almost nothing at that point. So, let us move on to another topic, this is string matching. So, supposing and this is of quite widespread importance in bioinformatics, though we are talking about only the simplest example here of exact matching. Supposing you are given a text of length n, so the text is called t, and you are given a short string s of length m, and find the first occurrence, or maybe find all the occurrences of s in t. So, supposing t is the text word Mississippi and the matching pattern is SSIP, then you should return the position 6, this is numbering from 1. So, I should really say 5, I am numbering from 0, 0, 1, 2, 3, 4, 5, it matches from here. So again, if you were to do it naively, it takes time order of n times m, because what you might do is check the first position, does it match. I mean, for each position here, if it fails to match, you're breaking, but if it matches, you are if you get a complete match in that position, you're returning it. So it may not be as bad as n times m, because very often you're terminating the inner loop before you finish it, but you're still doing a few steps of the inner loop. So depending on the nature of the pattern, the worst case could easily be quite bad. So there is an algorithm by Knuth, Morris and Pratt. I am not going to describe it in great detail, but the basic idea is that you can maintain what is called a lookup table, such that when you have a match that fails, that is this step here, it tells you, in this case m is incremented by 1, but instead you can increment n by some slightly bigger number, because it tells you if the match that began at m failed at m plus I, then where will the next possible match begin, and you can calculate that by basically calculating the position of each prefix of the match string in your full string. So it is a pre-computation that can be done in time order of m, and then using this lookup table you can search this text in time of order n. In fact, our maximum number of steps is like 2n, which you can show. So the total time is order n plus m. This is a quite widely used algorithm, and another called Boyer-Moore, which is slightly faster in terms of prefactors, but it is also order of n plus m, and this again is a whole field in itself, so I will not go into that. My last example for today is something called edit distance. So this is again a computer science problem, but it has analogies to biology problems. So the computer science version is given two strings, s which is of length n and t which is of length m. Find the minimum number of edits that will change s into t. That is, you could change one letter into another, you could delete a letter from one string, or you could insert a letter into one string, and this is kind of a distance metric between two strings, and it has a quite elegant solution in terms of something called dynamic programming, and the algorithm is basically define the distance dij as the edit distance between two substrings from 0 to I and 0 to j of the two input strings. So it is a partial edit distance, and in terms of these partial edit distances you can build up a full edit distance. So d00 is 0 because you got nothing to match. Then for each I and j you calculate dij based on the previously calculated values of I and j, which is I minus 1 j minus 1 plus the match score. So if these two match at these positions, the match score is 0, if they do not match it is 1, or you can insert, meaning your previous position is I minus 1 and j, and you can insert 1, the score of 1, or you can insert in the other sequence, that is also 1, and at each step you also place a pointer from this element to the element from where you calculated the value. For example, if I calculate ij from the value I minus 1 j, and I put a pointer there saying this is where I came from, and finally you fill the whole matrix and got the value d and m, and that is the minimum edit distance, and by following these arrows you can also get back the basic edits that you require. So here is an example. Supposing the two strings I have are carrot and parota with an O, like in Kerala, and I want to change a carrot into a parota with the minimum number of steps. So I start with 0, then each of these, the first row and the first column will have basically increments of 1, because I am adding a nucleotide here, adding a letter here. So this 1 comes from this 0, this 2 comes from this 1, and so on. So each of these cells had an arrow or arrows that I am not putting in here, sorry, but I have only marked out the important arrows. So, for example, now this guy, if I wanted, I could have put an insertion from C and it would have been a 2, or an insertion from here, it would also been a 2. Instead, I mismatch C and P and I still get a 1. It's a mismatch, but it's not as bad as a 2. So, I put a 1 here and I put this diagonal arrow. And then I actually have a match here. So, this 1 is better than this 2 and this 2. So, having made this match of C and P, all of these are terrible, but all of these come from here. This could in principle also come from here, and so on. So, we do not really care about that here, but for example, when you look at this 2 here, this is a match between CARRO and PARO, and it could have actually come from 2 possible places. The previous R could have matched, or there could have been a gap here and the R could have matched with the other R in caret. So, there were 2 arrows leading from here, but eventually you fill up the entire matrix and you end up with the T mismatching with an A. So, this 3 is 1 more than this 2. So, this arrow goes here and then you follow the arrows and you have 2 different paths that could lead you to the origin, and they correspond to these 2 possible edits. In the first edit, C is replaced with P and you put a gap here and a gap here. The second edit, again C is replaced with P, but the position of the gap here is different and this one is the same. So, if you want just one answer, you pick one arrow at random. Each time you have 2 arrows. If you want all possible answers, you have to follow all possible paths. This is as I said, called dynamic programming, but more complicated versions of this are used in aligning biological sequences, and in fact what I just described is called the Needleman-Wunsch algorithm in sequence alignment, where instead of simple zeros and ones, you have more complicated penalties. So, a match might still be a 0, but a mismatch might be some function of what A and B are, where A and B are 2 nucleotides or 2 proteins, 2 amino acids. And similarly, the gap might not be just 1, it might be some other number, and a gap extension might be different from just a gap. So, there is a big literature in this dating back to 1970, the paper by Needleman and Wunsch, but this is a fairly bedrock program in computational biology. Dynamic programming is the basic idea of constructing a solution from previously calculated solutions, is also used in other things like hidden Markov models, and there is a method called the Viterbi algorithm that tells you the most probable path through the hidden states. It is again constructed in the same way by taking partial sequences and constructing the full thing from the partial ones, and it is once you learn this technique, you might find new applications for it. Right, so that is about it for today. Next time we will overview a few third-party bioinformatics tools, and we will talk about how to use them effectively in actual biology applications. Right, thank you very much.